Good evening, students. So in previous class, we saw one approximate method, Rayleigh-Ritz method, which not only gives the fundamental frequency, but depending upon number of terms, functions we have chosen, we can able to get the more number of natural frequency. So we are choosing the eigenfunction in the form of series of functions multiplied by some constant, and through Rayleigh's quotient method we minimize those constants to formulate the eigenvalue problem of a continuous system. So basically with this, the continuous system get discretized into number of n number of degree of freedom depending upon how many terms we have taken in the series. So this is a way out for the solution of the continuous system eigenvalue problem in closed form, because in these approximate methods we are not solving the partial differential equation, but we are directly choosing the functions and then trying to get the natural frequency, similar to the procedure which we discussed in the discrete system. In the Rayleigh-Ritz method, one limitation is there that whatever the function we choose, they should be comparison function. That means its requirement is more stringent. It has to satisfy all the boundary condition of the problem, not only the geometrical, but also the natural boundary condition. Apart from that, it should be differentiable up to the P, which is L operators half of the differential order. So now we'll see, in fact, 2P and 2P it should be. And also we will see that whether we can able to relax this condition. Because what happens in, as we'll see, because at present we have taken simple boundary conditions and simple geometry of the system. But if we take more complex boundary condition, then even choosing the comparison function satisfying the all boundary condition and differentiable to 2P will be difficult. Sometimes it is impractical. So now today we'll see a variant of the Rayleigh-Ritz method in the energy form. So previous was we started with the eigenvalue continuous system eigenvalue problem formulation, but now we'll see that the energy form of the Rayleigh's quotient, Rayleigh-Ritz method, will relax this particular requirement of the choice of the function as comparison function. We can able to choose the basically admissible function and is having less requirement, which requires only satisfaction of the geometrical boundary condition and only differentiable up to P order. So one order less differentiation is required. That means it should not vanish up to the P order differentiation if we are doing that particular function. So now I'll share this slide so that so Rayleigh-Ritz method, re-examination of the boundary condition requirement. So yeah, As I mentioned, the comparison function required geometrical and natural boundary condition to be satisfied, and it must be 2p times differentiable. And so now we'll see whether we can able to relax this condition and satisfy only the geometrical condition, boundary condition, and it should be differentiable up to p times. That is we'll be choosing the admissible function instead of the comparison function. But the Rayleigh's quotient, as we defined earlier, need to be modified so that we, with this relaxation, our functions should not vanish in the Rayleigh's quotient. So this is one typical case in which taper rod is there is axial rod, it's vibrating axially, and at the free end there is a spring. So here two complexities there, that one is the varying cross section and there is a spring attached here, and axial vibration we are considering, or longitudinal vibration we are considering. So here this end is fixed and the spring other end is also fixed, but this end of the beam is free. The eigenvalue problem for continuous system of this kind of axial rod vibration case was we obtained earlier like this. We have boundary conditions here. One at x is equal to 0, the displacement is 0, and at x is equal to L, whatever the axial force is there is equal to the spring force, K into the displacement of the beam at the free end. So that is the spring force. So this is the boundary value problem. Now here we have two type of boundary condition. One is geometrical. This is the geometrical boundary condition. This is the natural boundary condition. So here satisfying the natural boundary condition is more difficult now, because we need to choose the function so that this should satisfy this condition also. If there's no spring, then the choice of the function is easier. But now with the complexity due to the spring, now choice of the u will be more difficult. So we know the L operator for this case, and M operator is this. And now we defined the Rayleigh's quotient earlier like this. This is we initiated with the eigenvalue problem, and we defined like that with the L and M operator, because L and M operators are there when we define the eigenvalue problem. So for the present case, the L operator is this. So substitute in the denominator part L operator. So minus is also coming from the L operator. Now this particular expression, which is there in the L operator form, we are doing the integration by part. Here we are doing integration by part once. So this is the first part, and then integration of the second part will give this limits 0 to L, plus then differentiation of this and integration of this. So that will multiply to give a square of that, and EAX will be here. Now here if you see, if you substitute this limits, x is equal to L, that is the free end. At free end, this particular axial force is equal to minus K UL. So if you put this here UK here, we will get plus, and K U square L will get from here. If we put x is equal to L, for x equal to 0, ux is 0. This is the ux is 0. So x is equal to 0 will not contribute any term here. Only due to the free end spring, we got this non-zero term. But for x is equal to 0, we are having there is no contribution because that term is 0. Then this is as it is. We are Now we are representing this as twice of Vmax. That is the potential, maximum potential energy as we defined the Rayleigh's quotient. Similarly, for the denominator part here, m is a simple function, so there is no problem here. Just we can keep that as it is, but there's no integration part required here because there's no differentiation here. Now we put back this and this in the Rayleigh's quotient. So this is the new Rayleigh's quotient. Now if you see here, the differentiation order of the u is single. In original form, the previous slide, the differentiation of the u was 2. So by doing the integration by part, we could able to reduce the order of differentiation requirement of the function by 1. So here, in this particular case, we require only differentiable up to the p. That is because here for XL dot case, the 2p is equal to 2. So in comparison function, we require the differentiation up to 2. But now, because of this part integration by part operation, we have reduced the order of differentiation in the integral by 1. So only p is equal to 1 requirement is here. And about the natural boundary condition, natural boundary condition is the force. That boundary condition has come in the form of the energy here. So implicitly, we could able to include the natural boundary condition in the energy term itself, in the Rayleigh's quotient itself. So there is no requirement of satisfaction of the natural boundary condition separately. Well, we choose the u function. So here you can see that the order of differentiation got reduced by 1. Also, the natural boundary condition automatically comes into the formulation. There is no requirement of that during the choice of this. So this particular form of the Rayleigh-Ritz method with this we can able to use the admissible function. So here we will choose minimizing sequence of function like this, where now we are using AI constants, which are adjustable constants, coefficients, and phi I is the admissible function. Admissible function is a requirement that should be only satisfy the geometrical boundary condition, and it is differentiable up to at least up to p times. So now let us see how the formulation changes because of this change. So now what we'll do, we will substitute this chosen sequence of function in the solution, in the Rayleigh's quotient. Basically, here this is the same Rayleigh's quotient expression. Now this is the choice of this. So ux will be replaced by wn in this expression. So wherever is there, so you can see we are replacing wn. Here also wn. Here prime is representing a derivative with respect to x 1 time. If there are 2 primes, then it will be differentiation with respect to s twice. So this has been replaced, ux and be replaced by wn. Now we are putting our series form of the solution in this expression. So now you can see k is there here because the multiplication of this function is there. So we are taking two dummy variable I and j, so that their multiplication can be we can able to do. So here I'm using the I and here j, but they're same terms because dummy variable can be changed without any problem. So this is representing the square of the Wm. at x is equal to L. So this is the first term. Then in the integration Ex as it is, this differentiation, if I differentiate this, because A is constant, phi is function of x. So if we differentiate this once, phi will get differentiation with respect to x. So that is shown here. This is the Wn square is there, Wn prime square. So here also I'm taking two terms, and differentiation with respect to x is on the phi I and phi j. A I and aj are the constant, so they will not get differentiated. In the bottom, we have the mx integration and then the square of this. So again here the square term of the Wn has been represented by two dummy variable I and j. So this is the Rayleigh's quotient when we substituted the series form of the comparison from the admissible function which we have chosen. Now we will rearrange that particular term. So here we are rearranging it. So if you see what we are trying to do, first thing is uh, we are bringing the summation outside, especially here in the summations are inside here. So I'm trying to bring out the summation outside the integral. So here brought out the summations. AI and AJ are constant, so they will not be within the integral. Remaining, which are function of x, will be here. Here there is no change, only the k I have brought in. K was outside. This is a constant stiffness, so I have here again I have taken out the summation outside. Integration and a, I, and j are constant, so they are outside the integration. Now I'm again clubbing this to the denominator terms, summing up this because this is common for both the terms. So I'm left with k phi I function of x, phi j function of x at x is equal to L, and then this integral. And in the denominator or numerator, sorry, this is the denominator. In the denominator, we have this I will put just in the bracket. Now I'm defining this term within the bracket as Kij, and this term within this bracket as Mij, and Kij is this from the here from the numerator, and Mij is from the denominator. So we have seen earlier the potential energy expressions generally we write in this particular form, and the kinetic energy we write in this particular form. So this Kij and Mij are the stiffness and mass coefficients. So here, as we have taken n number of terms in the solution, so we are discretizing the system into n degree of freedom system, and corresponding stiffness coefficient and mass coefficient can be obtained by this expression, which will form a matrix now. So we started with the continuous system, but using this, we discretize the system to n degree of freedom, and the corresponding stiffness coefficient and mass coefficients can be estimated from this. Now let us take, so in the previous example, there was a spring. Now I'm adding a disk also here. If I'm adding disk, what will happen? It will add to the kinetic energy term. So that means here, so if m is the mass of the disk, so this will be the kinetic energy part, in which T star part means omega square is removed from that. So this is the additional term which will come. Rest of the terms is as it is in the previous case, because we have one additional disk at the boundary. So that will contribute here, and the change in the will be there in the mass coefficient. So the mass coefficient will get changed, similar to the stiffness term. Now we have additional term in the mass coefficient also when we have disk here. So now you can see, so here whenever I'm representing this is a fully filled box, that means they are fixed. Suppose the empty box is the disk. So this is fixed end, this is also fixed end. So now you can see that how the boundary conditions are getting affected our mass coefficient and the stiffness coefficients. Now take one simple example. So this example is very simple, just to illustrate the method, and then we'll take up more complex case. So we know the cantilever beam. We have already solved for axial vibration. This closed form solutions are available, but just to check the method, how it works for simple functions, simple geometry, this particular example I have taken. So this cantilever beam is vibrating axially, is the fixed end, and there is no spring, nothing is there, so it is uniform. So here we are taking admissible function initially x, because, and we'll see whether this satisfy our requirement of the admissible function or not. And ux, then second time we'll take as x square, third time we'll take as x cube, and then in the last we'll take one comparison function. Comparison function, we know that this satisfies the all the boundary condition, but admissible function will satisfy only the geometrical boundary condition. So the Rayleigh's quotient in the energy form, which after integration by part, because now there is no disk here, no spring here, so those terms will not come here. Only this integrations will be there, as we formulated earlier, including the disk and the spring. So those terms are not there, so that has been removed here. Now, if we take the admissible function x, what is the requirement for the axial rod? It should be differentiable at least up to p is equal to p. So p is 1 for the case of the axial rod case. So if we differentiate this once, we get a constant quantity 1. So that means it is satisfying the requirement of the differentiation. What about the boundary condition, geometrical boundary condition? We know that at this end, fixed end, displacement should be 0. So if we put x is equal to 0 here, so is satisfying that is 0. We are not bothered about the natural boundary condition here in the admissible function. So once it is satisfying the one of the whatever the geometrical boundary condition is there, then we are happy with that. Now we'll substitute this function in the and here at present I'm taking only one function. I'm not taking two functions. So I'm just trying to find out only the fundamental natural frequency. So here in the Rayleigh's quotient, in the energy form, so if we substitute here, because there is a differentiation with respect to x is there, so that will be 1 square of that, and here x square, because x is there, so square of that will be x square. So if we integrate this, we'll get this, and the x cubed by 3, and if we solve, we'll get 3a by ml square, and if we take the square root, we'll get the natural frequency, fundamental natural frequency of this system is 1.7321 under root a ml square. So this is the natural frequency we got by just taking the simplest admissible function. And now this is the exact solution which we already obtained using eigenvalue problem solution, closed form solution. So the fundamental natural frequency is pi by 2 and this. So pi by 2, if you do simplify, this is 1.5708. So some deviation is there, around 0.2 deviation is there, or 0.15 deviation is there, but it's quite close. Yes. So see, just by choosing a simple function, we could able to achieve some solution of this Now I will take the x square. So if we take s square, so here anyway this will satisfy the geometrical boundary condition and the differentiable up to at least one order differentiation, that is no problem. So if we differentiate, we'll get 2x here, and here this will be x4. The square of that, if we simplify, we'll get 20 a by 3 ml square, and if we integrate, if we take the square root, we'll get 2.58. So here, uh, as compared to the exact one, is deviating more. So even we took the higher order, higher degree polynomial, the solution is deviating more. So let us take the x cube. If you're taking x cube, because this is also satisfying the geometrical boundary condition, and anyway this is at least differentiable up to p is equal to 1. So if we substitute p x cube here and simplify, we'll get 3.5496. This. So here is deviating much more. So that means what is happening here, with admissible function, if we are increasing the order, then it's not necessary that we improve the solution. So even this x is giving much more accurate result as compared to that. Now let us take the fourth case. If we take a comparison function, which is just a quadratic. So I've taken the comparison function this, because comparison function need to be satisfied both the natural boundary condition and the geometrical boundary condition. So let us see whether it satisfies or that or not. So at x is equal to 0, u is 0. So if we substitute x is equal to 0, this becomes 0. So this is fine, geometrical boundary condition. For x is equal to L, because this is free end, this force should be equal to 0, which involves the derivative of this. So I have taken the derivative of this, so I get x minus L. So if we put x is equal to L here, I'm getting the 0. So that means this is also satisfying the natural boundary condition. So this comparison function, this is a comparison function now, and it should be differentiable up to 2p twice. So that means if I differentiate this once more, I'll get a constant quantity 1. So that means it is satisfying the second requirement also. So we cannot take linear here, because linear, then it will not able to differentiate up to 2. It will vanish. It will become 0. So that is the requirement for the comparison function. So if you substitute this in the place of u and differentiate, and then in the denominator also take square, you need to square it and integrate, simplify it, you'll get 5 by 2 a ml square. If you take square root of that, you'll get 1.5811. So now if you compare with the exact one, this is much closer as compared to even x, the very first case also. So here you can see that the comparison function, when we are choosing which is satisfying not only the boundary condition at this end and this end, then the accuracy is more. And of course, if we take the eigenfunction itself, then we'll get the same value of both. So, but eigenfunctions for this case is simple, but for more complicated case, as we'll see in the subsequent example, we cannot have the eigenfunction or even comparison function choice also will be difficult. But this was simple cantilever case, so we could able to choose this relatively easy. So this was one of the example. Now the previous example was for the axial vibration. Now we'll take up the more complex case when we have the transverse vibration. Transverse vibration, in which we have, if we are taking the cantilever case same as the previous one, then we have the two boundary condition at the fixed end, displacement should be 0 and slope should be 0, and two boundary condition at the free end. Bending moment should be 0 and shear force should be 0. So now choice of the comparison function will be more difficult here. The previous comparison function for axial rod case will not be satisfying this requirement here. We need to choose differently, or we need to choose the admissible function, which only we need to satisfy the two geometrical boundary condition. We will not bother about the natural boundary condition. So let us first take the L operator, M operator. L operator here is we have fourth order differentiation. Now if we substitute in the numerator part of the Rayleigh's quotient, L operator. So L operator I have substituted here. Now, as we did for the axial rod case, we'll do the integration by part to reduce the order of differentiation of the u within the integral. So here, if we do integration by part twice, so this is the first part, integration of the second part, 0 to L, minus differentiation of the first part, further integration of the second part, plus further differentiation of the second part, this, and the integration of the second part. So I did the integration by part twice in single step. Now we'll see the boundary conditions. Here at x is equal to L, here this shear force will be 0. So this quantity will be 0 for x is equal to L. For x equal to 0 at the fixed end, we have ux is equal to 0. This is 0. So this term is 0 for both x is equal to L and x is equal to 0. Similarly, here at x is equal to L, we have bending moment 0 and x is equal to 0 and the slope is 0. So for both the x is equal to L and x is equal to 0, this also will be 0. Why they are becoming 0? If we have some spring or mass at the free end, then they will not be 0. But now we have taken simple boundary condition of the cantilever, so that's why these two terms are becoming 0. And this is the integration. This term will be left out. So this is the final term which will be left out among after doing the integration that part. For the denominator part, M is simple operator, so function. So this will be as it is. Now the Rayleigh's quotient will take this form. Now if you see here, earlier the order of differentiation now of the ux was 4, now it is 2. So that means when we choose the ux, even we can choose the admissible function which is having or the beam case requirement of the 2 times differentiation. In the beam case, the comparison function is having a requirement of 4 times differentiation because 2t is equal to 4. So now you can see that we reduce the requirement of this function by 2, so that whatever the function will choose, that should be differentiable up to the 2 times only for the beam case. Okay. For axial case, we know that for admissible function only 1 differentiation is required, and for comparison is 2 required for axial case. But for beam case, requirement is one differentiation more is there. So now when we choose our solution in the form of series, having phi as a admissible function and a are the constant, and if we substitute similarly in place of uxw, and double prime here is coming, which is representing that differentiation with respect to x is twice. In the axial rod case, it was a single prime, but now it is here double prime is there. This term remains the same as previous one. Now we'll substitute this series form here. Now you can see that when we differentiate twice this wn, the differentiation will come to the phi I. AI is constant, that will not take differentiation. So here square term is there. So this is corresponding to I is equal to 1 I. This corresponding to J. And differentiation when the phi is appearing in both cases twice. In the denominator, we have the same as it is the function we have kept. Now we'll take out the summation outside and bring the integral inside. We'll keep all the terms containing function of x within the integral and outside which are constants. So here that has been done. So all the constant we have taken out because they are having I and j subscript, so they cannot be out of the summation. They will be within the summation. So now and here all the terms are having function x here also. Now the same thing I have written here, but I have put them in a bracket. The integral term put them in a bracket, and this bracket term I am representing as kij, and here mij. So now you can see that kij is representing double derivative of the phi's, and mij is representing similar to the previous one. Here the change is there as compared to the axial rod case. It was EA. Here it is EI because this banding is there. So I term will be coming in axial rod case because this is axial force. So EA comes capital A. So this is the now coefficients for the cantilever simple case. At present, we are not considering any spring or disk, other things. If we consider, changes will come correspondingly in this coefficients. So this is the case in which now we are introducing a spring. Now because this is a banding vibration, so the spring has to, so this spring will take, it will restrict the motion in the vertical direction. In this axial rod case, the motion was axially, so spring was attached along the direction of the beam. But now because it's vibrating vertically, so we have put the spring K like this. With this addition, we will be having similar term as the previous case. This additional term will come KUX. So as we go back, so if we satisfy this boundary condition, if we go back, so this is the shear force which we equated to 0, but now this will be replaced by KUX. So this will be giving us this term at x is equal to L. So this is the additional term which is coming because of this. Now again, if we substitute this here and here, so this is corresponding to the spring part, this is corresponding to the beam part, and this is corresponding to the beam part mass. There is no additional disk here. So now again we'll take out the summation outside and then integration summation outside, then even summation we can take common. So here if you see, this is similar to the previous axial rod case. Only thing is here this is a double prime, and instead of EA not is EI. This remains same. So within this bracket term I am representing that as Kij, and this is Mij, which is defined like this here. So these are the two the coefficients which we need to calculate, and here I and j will vary from 1 to n. So we'll be having n number of such coefficients, or n into n number of such coefficients, which will form the stiffness matrix and the mass matrix of the discretized continuous system. Okay, so the same example which we took earlier for the axial rod case, and now I'm taking for the bending case. I'm taking now because the requirement of the admissible function is higher here. So I cannot take x here as admissible function. What will happen if we put x only? This will become 0 because this differentiation with respect to x is twice. So minimum we can start with the x square as an admissible function, and x square, whether it satisfies the this two boundary condition. Now we have two geometrical boundary condition which we need to satisfy. So if we put x equal to 0, x square becomes 0, so it is satisfying the first boundary condition. Second boundary condition, the slope. So if we derivate this once, this will be 2x, and if we put x is equal to 0, 2x will become 0. So it is satisfying the second geometrical boundary condition also. So now you can see that the slope, this is the slope here in the bending case. In the axial rod case, it was showing, it was giving us the axial force. So it should not confuse with that. So here this is a geometrical boundary condition for the beam case. So minimum we can take x square as the polynomial term as the admissible function. And second case will take x square and x3 together. Two terms will take. So when we are taking two terms, we'll see that how we can able to get the two natural frequency. So case one. So case one, only single term we are taking. So once we are taking single term, this is the same as the Rayleigh's quotient energy form. So there is no when we take two terms, then Rayleigh-Ritz method comes, in which we minimize the coefficients A1, A2 like that. So here we are substituting. So here instead of u, I'm putting phi1, and phi1 we know is x square. So x square, if we put here, if we differentiate twice, we'll get 2 here, and here x square of square, so that will give x raised to 4. If we simplify this and take the square root, we'll get 4.4721 EI by ML4. So this is for bending case. So this expression will be different. Even the number will be different as compared to the previous one. But for bending case, the cantilever case, we had the first natural frequency this much. Bending case, so 3.5, and here 4.4. So some deviation is there, but at least is giving some value which is upper bound of the first natural frequency, as we always get the with the Rayleigh's quotient upper bound for the fundamental natural frequency. So with the single function we got only one natural frequency. Now we are taking the two functions. So a1 phi1x function of x, a2 function phi2 function of x. So a1 x square plus a2 x cube. X cube is also satisfying the both the geometrical conditions as we have checked for the x square. So this is a combination of two admissible function. They are differentiable at least up to 2p, and they are satisfying all the boundary conditions at the geometrical boundary conditions. So now let us see how we can able to obtain the coefficients, mass coefficients. So earlier we obtained the expression for the mass coefficient. So here we have I and j is equal to same, equal to 1. So M11 is, so correspondingly phi1 and phi1 will be there. Phi1 square, phi1 is x square. So x square square, if we integrate, we'll get this. Similarly, M12 is mx phi1 phi2. So the changes here, phi1 phi2. So whatever the subscript is there, so even if 2 and 1 is there, they will interchange, nothing will change in this. So now phi1 is x square, phi2 is x cube. So if we integrate this, we'll get, sorry, this should be L, this should be L, all should be L. Okay. because this has been already integrated, so there should be L. So they all should be L. Similarly, M22, then here phi 2 square will be there. Phi 2 is S cube, X cube. So we'll get this. Now we got all mass coefficient, so they can be put in the matrix form. All this, and this is symmetric, so we got the mass matrix from this. Similarly, the stiffness coefficient can be obtained. Here EI phi 1 double prime, phi 1 double prime, K11 will be 1, 1. So if we differentiate phi 1 twice, we will get 2 and 2 square. So basically, because both are same, 2 square, so this will get 4 EIL. K12 phi 1 double prime, phi 2 double prime. So phi 1 double prime is 2, phi 2 double prime will be 3x because 6x, because x cube, if you differentiate twice, you get 6x. If you integrate, you will get this. Similarly, K22 differentiation of phi 2 double prime and the square, 6x square. So that will give this. So now we got the stiffness coefficient of the, so we can form the matrix on these. And here also is stiffness matrix is symmetric. Now we have the eigenvalue problem. This is the stiffness matrix, mass matrix, similar to the discrete system now. So K minus lambda M, and so we can able to take the determinant of this K minus lambda M, and if we take determinant, solve for lambda, we'll get 2 roots of that. If we take the square root of that, we'll get 2 natural frequency from that. So first natural frequency is 3.5327, this constant, and omega NF2, second natural frequency 34 this. So now if you compare the first natural frequency is the exact solution from the actual eigenvalue problem. This second natural frequency exact from the eigenvalue problem. Now if you compare, the first natural frequency got improved drastically. It is not quite close. Second is having much difference. So what is happening when we took single uh, single term earlier, then the deviation was more in the fundamental frequency. But when we took 2 terms admissible function, then the first natural frequency became closer. We got second natural frequency also in this, but it is deviating more. But if we take 3 terms, we'll form 3 by 3 matrix. Then we'll see that the first will become much closer to the exact one. Second will come more closer to the second one. Third will be having more deviation. The third higher natural frequency having more deviation. So this trend will be generally be there. Key higher and higher natural frequency will be having more deviation, but if you're taking more and more term, lower natural frequency will be converging to their actual values. So that is generally called convergence. Now, from the previous thing, once we got the eigenvalue, we can get the eigenvector also. So eigenvector, this is corresponding to the first natural frequency eigenvector. This corresponding to the second natural frequency eigenvector. These are what? If we go back to the over this, these are the basically in the Rayleigh-Ritz method. These were the constants which we chose in the series which we chose. So these are the A1 and A2 in the series. So that means U1 we have chosen in the as a1 x square, a2 x cube. This is corresponding to the first natural frequency. So I substituted 1 here in place of a1. Superscript is representing the first natural frequency. A2 I have substituted this in place of a2. So this is the mode shape corresponding to the first natural frequency. Similarly, for the second natural frequency, this correspondingly 1 I substituted here, and a2 I have substituted this. So this will be the second natural frequency. So here, these coefficients which we got the eigenvector, they're not the mode shape. They're the coefficients, relative value of the coefficients. Once we put them in eigenfunction. So this is the eigenfunction for the first natural frequency. This is for the second natural frequency. In this polynomial form, they look very vague, but if we plot them, then things will be more clear. So now, when we took the two additional function, we got the natural frequency first like this, and second, this is the mode eigenfunction corresponding to that. This is the second natural frequency, and this is the eigenfunction corresponding to that. We have solved the cantilever beam, uniform beam, and the transverse vibration. So now this is the mode shape, first mode shape. This is the fixed end, this is the free end, and this is the relative displacement of the beam. So this is the trend. So now you can see here, both the displacement is 0 here, and slope is also 0, because by choosing the admissible function, we ensured they satisfy the geometrical boundary condition. So you can see the slope is also 0. To draw the tangent to this curve at x is equal to 0, that slope will be 0. So this is the first mode of the beam will look like. This is the second mode. So this function has been plotted from 0 to L. So now you can see the second mode is having this behavior. Here, the geometrical boundary condition that displacement is 0. Also, this, if you draw the tangent to this curve at x is equal to 0, slope will be 0. So that is satisfied here. But what is happening here in between? There is a node. So when this beam will vibrate, this way there will be a node here. In other extreme, it will come here and it will vibrate like this. So this point will always be fixed. This part and this part will go up and down, but this is called node of the beam. So this behavior is seen that as we increase, if we are vibrating this beam with the second natural frequency, there will be one node here. If we go for the third natural frequency, there will be two nodes. So one here and another more closer to the free end. So, and how we can able to get the three natural frequency? We need to choose the three admissible function like x square, x cube, x4, or any other function. So by that way, we can able to get the third natural frequency and corresponding mode shape also. So I'll stop here. So this example, I hope the Rayleigh-Ritz method with the re-examination of the boundary condition requirement, how the admissible function can be helpful in solving more complex system is illustrated here. So we'll take more examples as we progress, more complex beam shape and boundary conditions. But if you have any questions, you can ask on the today's lecture. Mainly today I explained the examples, so if you have any doubt in any steps, you're welcome to ask. And I hope people are doing assignments, because that is very important. 30% weightage is there. So I expect that everyone should complete all the assignments so that because in the quizzes that many detailed steps we cannot ask in the online mode, but if you do through assignments, and if your doubts, several people are asking also, even during the formulations of your doubts, you are welcome to ask so that your concepts are clear regarding the subject. Because unless you do the assignment, is very difficult for you to comprehend the overall subject. Okay? Because in quiz, we cannot able to check that particular aspect, and that's why 30% weightage is given, and that will change the grade like anything. If you lose the 30%, then you'll lose the grade like anything. Okay. So I again advise, please do the assignments. That is all important. And another thing regarding the next quiz will be on 16th November, Monday. That will be on the approximate methods. Whatever I'm covering and whatever the assignments I've already given, for that I think 8 is the last date, but maybe I will extend for 4 new days. So for approximate method, we will have quiz on 16th November. So with that, I'm stopping here.